Hi everyone, this is our third and final lesson on the topic of rigid object rotation in viscous flows. I'm going to briefly discuss another aspect of rotational kinematics, namely revolution, but my main focus today is on mechanical aspects. Let me first review the rotational behavior of rigid objects in viscous flows. I will start with the spheroids in monoclinic flows. Monoclinic flows can be described by a velocity gradient tensor like this. In the coordinate system XYZ, the shear plane is parallel to y-axis. The shear strain rate is gamma dot. The strain rate parallel to x, y, and the z-axis are respectively epsilon x dot, epsilon y dot, and epsilon z dot. The vorticity is parallel to the z-axis. The vorticity normal section is xy plane. The orientation of a spheroid object is defined by a theta angle, that is a trend of its distinct axis, and a phi angle, that is the orientation of the distinct axis from the vorticity vector. So here is an equal area projection of the geometry of the problem. The problem can be described by three dimensionless parameters: the sectional kinematic vorticity number, or a recast of the sectional kinematic vorticity number by a characteristic angle. The positive and the negative sign is related to the relative magnitude of epsilon x dot and epsilon y dot. Please read chapter 9 of the lecture notes for details of this. A second dimensionless number is lambda, which is a ratio of the sectional kinematic vorticity number divided by the shape factor. The third dimensionless number is z, that is the ratio of strain rate along the vorticity axis divided by the shear strain rate. So this problem has analytic solution, and the analytic solution is expressed by these composite equations. The equation for theta is this one. Depending on the parameter lambda, the theta expressions are different, so the behavior is quite rich. The expression for phi angle is this one. Because we have these analytic solutions, we understand the rotational behavior of spheroids thoroughly. In the more general situation, the rigid object rotation must be solved numerically. And the problem can be stated by this set of equations. The first equation is the differential equation for rotation. The second equation is a statement for the angular velocity based on Jeffreys' result. And the third equation states the initial condition of the object. So we often say that the rotation of rigid object is an initial value problem because it depends on the initial condition. The numerical solution has been implemented in MathCAD and MATLAB. Another kinematic aspect of rotation is revolution. Revolution has things to do with inclusion chair microstructures. Thin kinematic porphyroblast, such as garnet, can encapture a foliation in its crystal. And these are the inclusion chairs. We see a snowball garnet develops when the garnet grows over an external foliation. Spherical objects have relatively simple rotational behavior. The rotation axis is always parallel to the vorticity axis, and the sense of rotation is always the same as the vorticity. However, elongated porphyroblasts, revolution can be very complicated. Here I explain why the revolution of an elongated object can be complicated. Object A and B are prolate. A has an initial plunge to the east, and B has the initial plunge to the west. The rotational path of A is this one. In a monoclinic flow, A rotates along this path and eventually stop at the vorticity normal section. The rotational path for B is this one. It also stops on the vorticity normal section at a fixed position, depending on its aspect ratio. However, the sense of rotation of A and B are opposite, even though the flow is the same and the object shape is the same. From this simple example, we understand that the inclusion chair geometry will be very, very sensitive to the initial conditions of the object if the object is not a spherical one. And we can understand this from the angular velocity expression of Jeffreys. For spherical objects, the angular velocity is only dependent on the vorticity because the second term vanishes. For a triaxial object, for an elongated object, prolate as well, the second term is non-zero. The rotation path is sensitive to the initial condition. So the conclusion is that the revolution of elongate objects is complicated and their inclusion chairs are not easy to interpret. So much for the kinematics. I'm now going to move on to forces on a rigid prolate object. The viscous matrix exerts forces on the embedding rigid object, and that results in stress in the object. If the stress reaches the tensile strength, the object may fracture, polynoid structures may develop. On the other hand, if the force reaches the buckling load, the object may fold. Based on Jeffreys' equations, forces acting on a prolate object in simple shear gives rise to the following stresses on the section normal to the long axis of the object. So the normal stress is this one, the shear stress are these expressions. RE refers to the aspect ratio. Theta is the trend of the distinct axis with respect to the shear zone boundary. And phi is the angle of the distinct axis with respect to the vorticity. Phi equal 90 degrees means the object long axis is on the vorticity normal section. So we'll concentrate on the normal stress in the longitudinal orientation of the object. Here is a schematic diagram showing the flow on the vorticity normal section. So in this case, phi is 90 degrees, so this term is 1. When theta is 45 degrees, the longitudinal stress is tensile. When theta is 135 degrees or negative 45 degrees, the longitudinal stress is negative. In either of these two situations, shear stresses are zero. Of course, this is well known. This is the magnitude of the longitudinal compression, and this is the force of longitudinal extension when phi is 90 degrees and theta is 45 or 135. If this compressive stress reaches a magnitude, the Young's modulus divided by the flow stress, the shear stress of the fluid, then the object can buckle. On the other hand, if this force reaches the tensile strength of the object, polynoid structures may develop. In rocks, we see microbouldins of elongate hard minerals very often. Microbouldins of tourmaline in malanites are very common. Here are pictures from granitic malanites from the Chongshan Metamorphic Zone, Yunnan Province, China. It's from Li et al., published in 2020 in Journal of Structural Geology. It's very, very interesting to look at the morphology of these microbouldins. Commonly, the elongate direction of these minerals, the elongate minerals, are close to parallel to the stretching lineation of the malonite. So the stretching lineation is close to being horizontal here in this diagram. The tensile fractures develops in all different places. The tensile fractures can be very, very closely spaced. The fractures can develop in different places, almost randomly in the crystal. Keep that observation in mind. Now let us review the two popular models for the development of microbouldins. One model is called the shear lag model. The shear lag model is schematically shown here. A strong fiber phase is embedded in a weak phase here, and the overall deformation is pure shear in the direction of the fiber axis. B is the situation of the overall deformation if there were no fiber present. Vertical lines are markers, horizontal longitudinal extension and homogeneous deformation. Because there is this stronger fiber there, the deformation is now heterogeneous. Shear stress develops on the interface between the weak face and the fiber. Shear stress is 0 in the middle, but increases progressively towards the end. The normal stress in the fiber is, however, maximum in the middle and minimum near the end. If the tensile stress reaches tensile strength of the fiber breaks. So the fiber is expected to break in the middle point. When the fiber fractures from the middle point, it separates into two shorter segments. The aspect ratio is increased. The process continues. So the fiber may break into two and then two into 4 pieces. So it's a middle point fracturing, successive middle point fracturing. That's the shear lag model. Do we see successive middle point fracturing in rocks? A, B, C here are tourmaline in quartz from monazite, and it's taken by different people. The fractures are not really in the middle, so they are random. They could be anywhere. D is a picture from another mineral, piedmontite. So the fracturing again doesn't appear to be in the middle point. Some more pictures of microbudens of tourmaline in monazite from Goligang Metamorphic Belt, Yunnan Province. So tourmaline here, the fractures here. These fractures do not occur as middle point fracturing. They occur randomly. Because of this difficulty, Shaochen Ji proposed another model called near-end fracturing. Instead of middle point fracturing, the fracturing is always near the end of the mineral. However, I do not see that these fractures develop always from an end. Fracture develops, to me, it's randomly anywhere. So, neither middle point fracturing nor near-end fracturing explain the observations. I think a better explanation is provided if we consider stress in a strong phase due to the viscoelastic interaction between the matrix and the object. A more thorough analysis of this will require Eshelby's equivalent inclusion approach. However, the main result can be discussed in the context of rigid object in viscous flows. The result is this. The longitudinal stress in the fiber in the Proulet object divided by the shear stress of the fluid is related to the aspect ratio of the object, of course, and it's also related to a viscous effect. It relates to time. It's not an instantaneous thing. T here is the dimensionless time. It's actual time divided by the viscous relaxation time. This is from Jeffrey's result. So if we do not consider the viscous effect, do not consider the viscoelastic interaction, make this T very, very large, the viscoelastic solution converge with Jeffrey's solution. If we consider the viscoelastic interaction, the Proulet object is elastic. It has an elastic shear modulus. The matrix is viscous, as in viscosity. The 2 defines the relaxation time. For geological materials, say the matrix is quartz feldspar malachite, and the object is a strong mineral, like a feldspar, a tourmaline, or whatever strong mineral. The relaxation time could be tens, hundreds, or thousands of years, depending on the relative magnitude of these 2 parameters. So, because of the time effect here, neither the loading or unloading is instantaneous. Although fracturing is instantaneous when the tensile strength is reached, fracturing does not release the stress instantaneously. So fracturing can continue in the prolate object. This means that when you develop a fracture, you don't relax the stress in the strong mineral immediately. So nearby fracturing can continue developing, and that is the key for the development of microbuoyant structures in strong minerals. So the main points are summarized here. When tensile stress reaches the tensile strength, fracture develops. However, this does not relax the stress instantaneously. Neighboring tensile fractures can still develop. Also, fracture growth can be slow in geologic conditions. So multiple parallel fractures can grow at the same time. These tensile fractures are actually controlled by the geometric irregularities and the mechanical flaws in the grain, leading to essentially random distribution of the fractures. This, I think, explains why we see random occurrence of fracturing. The viscoelastic model I just presented for the development of microbuoyants has potential application for the microbuoyant piezometry. The principal result is this one, expressed in this equation. The stress in the object normalized against the shear stress in the matrix is related to the shape of the object and the dimensionless time by this equation. If the stress in the object reaches the tensile strength of the object, microbuoyants will develop. This equation can be plotted in a diagram like this. The vertical axis is the shear stress normalized against tensile strength, and the horizontal axis is the effective aspect ratio. This equation, when dimensionless time is sufficiently large, will give a plot at this purple curve. The purple curve divides the space into the upper domain and the domain below the curve. Any object that plots above this purple curve are expected to be Boudienaged because the stress in the object will be beyond the tensile strength. If an object plots below this purple curve, the object is expected to be still intact. Therefore, if we identify the critical aspect ratio, the critical aspect ratio should plot on this purple curve. Therefore, if we can identify a field situation in a single shear zone, for instance, if we have microbuoyants developed in multiple phase minerals. For instance, we have a malonite microbuoyants are developed in feldspar, tourmaline, OPX, etc. If we are able to identify the critical aspect ratio for each of the different phases, they are expected to plot on different locations on this purple curve because they have different tensile strength. If we can identify a field area like that, that has the potential to solve not only for the differential stress of the shear zone, but also for the tensile strength of the different mineral phases for the condition of natural deformation. Piezometrical result obtained by this method is self-calibrating because we are relying on multiple microbuoyants. And also, we would be able to get the tensile strength for different mineral phases under natural deformation conditions. This method means that for each mineral phase with microbuoyant, we can establish an equation like that. If we have 3 different phases, we'll have 3 different equations. We can solve the equations simultaneously to get not only the shear stress of the matrix, but also the respective tensile strength for each phase. I have covered various topics of rigid body rotation in viscous flows. More details are presented in the lecture notes, specifically Chapter 9. So I recommend you read Chapter 9 if you want to get more details. That's it for this lesson. Thank you for your attention.